Hello everyone, welcome to the ITCS talk on an algorithmic bridge between Hamming and edit distance. I am Barna, Saha, and this is a joint work with Elazar Goldenberg, Tomasz Kociumaka, and Robert Krauthgamer. This is the outline of the talk. We'll start with an introduction by motivating the problem that we study in this paper, followed by the main technical contribution of this work, and then I will wrap it up with some open questions. Well, this work is about sequence comparisons. In many applications, we measure similarity between strings. These applications include computational biology, where you have to measure similarities between DNA and RNA sequences, pattern recognition, text processing, information retrieval, and so on. Two main measures of sequence similarities are Hamming distance and edit distance. In Hamming distance, you compare character by character and you are looking for substitutions, minimum number of substitutions that can convert X into Y. So in the first example, in the example on the top, Hamming distance is 3. In edit distance, in addition to substitution, you also allow insertions and deletions. So another way of, if you are using edit distance, to convert X to Y could be like you delete this C, you insert this C over here, and you substitute this H with a K. So with 3 edits, you can also convert with 1 insertion, 1 deletion, and 1 substitution, you can also convert X to Y. So edit distance is 3. Of course, you could have done just 3 substitutions in this case to convert X to Y. Here is another example where if you are only allowing Hamming distance, you have to substitute 7 characters out of 10. So Hamming distance is 7. Whereas for the same example, like if you are allowing insertion and deletion, you can convert X to Y just by doing 2 edits. You just have to delete this P and insert this K over here. So with 2 insertion and deletions, you can convert X to Y. So edit distance is much more versatile, much more robust, and it gives you the real similarities and differences among sequences. However, Hamming distance is cheaper to compute. You can compute Hamming distance in linear time. You can approximate Hamming distance with arbitrary precision in sublinear time. Whereas for edit distance, exact computation of edit distance requires quadratic time unless strong exponential time hypothesis is false. And also like sublinear time complexity of edit distance, like we don't have any constant factor approximation, for example, that can approximate edit distance in sublinear time. So there is a huge gap between computational complexity of Hamming distance and edit distance. So what makes edit distance so hard? Well, insertion and deletions gives you much more flexibility and makes your algorithm design much more harder. Indeed, and these are insertion deletions are in short called indels. These are really needed for real-life sequence comparisons. However, in many practical applications, the number of indels are much fewer than number of substitutions. You can look into our ITCS paper where we have provided multiple references. They are mainly coming from computational biology, where the differences in the sequences are predominated by number of substitutions, though there are few indels that need to be handled. So the questions that we are asking is like, can we design faster algorithms for the case of edit distance with few indels? Is it more like Hamming distance or is it more like edit distance? Can we provide an interpolation between the complexities of Hamming distance and edit distance from linear to quadratic by modifying the substitution to indel ratio? To do so, we define new metric. One is where we assign different cost for substitutions and indels. Substitutions are cheaper, indels are expensive. So for example, you can assign a substitution cost of 1 over 10, whereas 1 indel will cost you 1. So this naturally favors more substitutions, 10 times more substitutions than indels. Or there could be another way of modeling these scenarios that you assign different budgets for substitutions and indels. Say you ask, hey, return me an alignment with KS substitutions and KI indels, where KS is much higher than KI. In the paper, we consider both these different ways of modeling substitution versus indels. But in this talk, I'm going to focus on the first one, where you assign different costs, substitutions are cheaper, indels are expensive. And precisely, we define this new metric EDA. A is a parameter greater than equal to 1 integers, and EDA xy is the minimum cost of edit operation needed to convert x into y, where substitution cost 1 over a and indel cost 1. Here is an example. If you set a equal to 2, so substitution cost 1 over 2, which is half. In this example, if you delete this a and if you add this b over here, so with 2 indels, you can convert x to y. So indel cost will be 2. Here is another way of converting x to y, where you do a substitution in the first character, a to b, then a substitution over here, b to a, another substitution here, a to b. So with 3 substitutions, you can also convert x to y. And what is the cost of 3 substitution? That is 3 over 2. So 3 substitutions is cheaper than 2 indels. If a is equal to 1, well, in that case, you get back your normal edit distance. Everything has uniform cost in that case. On the other hand, if you set a equal to n, the length of the string, then substitution is so much cheaper that you don't want to have any insertion deletions at all. So now you are in the Hamming distance regime. Therefore, by varying a, you can have a nice interpolation from Hamming distance to edit distance. A equal to 1 is edit distance, A equal to n is Hamming distance. And what are the algorithmic challenges? The algorithmic challenges are to interpolate between the computational complexities of known algorithms for Hamming distance, linear time, and edit distance, quadratic time, find good approximations for EDA, possibly in sublinear time. And then from computational complexity, we want to understand whether it's possible to provide lower bounds for EDA, and if that lower bound also kind of interpolates between Hamming and edit distance. We look into all of these in this paper, and our main contributions is to provide an 1 plus epsilon factor approximation for EDA with a sublinear running time for suitable choice of parameters. Here I should mention, irrespective of the choice of parameters, getting a polylogarithmic approximation for normal edit distance in sublinear time, we don't know how to do that. So there is a big gap here between like what we can provide in this paper, what we can provide for EDA and what is known for normal edit distance. So we can do so much better for EDA compared to edit distance. Of course, it depends on the value of A, because if A is equal to 1, we get back normal edit distance normal. So that's why this is sublinear running time for suitable choice of parameters. But we should mention, we should remember that irrespective of the choice of parameters for normal edit distance, we don't know how to do that, even close to that. In addition, we also provide algorithms for exact computation and show tight conditional lower bounds for EDA. For 1 plus epsilon approximation factor, this is the running time we get. It's n over a epsilon cube plus a k cube. What is k? K is the optimum EDA distance. It's in this new definition of edit distance between x and y. So you can see if a is large, that is, there are many substitutions, and k is not too large, then this is sublinear running time. If suppose a is n to the 1/4 and k is strictly less than n to the 1/4, then we get a sublinear running time. And how should you set the value for a? Well, a good value for a will be the substitution to indel ratio that you are expecting in your application. Okay, so now let's look into this theorem. And I will try to give you some main ideas like what behind this theorem. Well, the goal is like we are given x and y, which satisfies the EDA is less than equal to k. And we want to find an alignment with cost 1 at most 1 plus epsilon times k. Here is an observation which is simple but crucial for our algorithm. That is, we can allow epsilon a substitutions between consecutive indels, since epsilon a substitutions only cost an additional epsilon cost, right? Because for every substitution is 1 over a cost. So epsilon a substitutions overall will cost an extra epsilon in the cost, which can be absorbed in one indel because one indel cost 1. And we are fine with 1 plus epsilon approximation. So essentially, epsilon substitutions are, you can do those for free when you are considering EDA and you are looking for 1 plus epsilon approximation. Another important ingredient, which has been very crucial for the development of normal edit distance as well, is LCE queries, longest common extension queries. So what is longest common extension query? Like you are given 2 strings, capital X and capital Y. You are also given 2 positions in those 2 strings, small x and small y. If you want to answer LCE DXY, that is the largest substring starting at small x and small y, which has Hamming distance strictly less than d. Okay, so for example, if you are looking for LC3 query, you see that is 4, because like if you're looking at substrings of length 5, then there are 3 mismatches. So therefore, the longest that you can go from starting at x and y with strictly less than 3 mismatches is 4. So LC3XY is 4. We can have an approximate notion of LCE queries, which is given by LCD, C, which is any value between LCD query and LCCD query. So for example, LC3XY is 4, as we saw in the last example. LC6XY here is 10. So LC3, 2 can return you any answer between LC3 and LC6, that is between 4 to 10. So that's how you can approximate. You can have an approximate version of LCE queries. This LCE queries, once you know how to compute this LCE queries, you can use them to compute edit distance. Let's look at normal edit distance, how you can do it. So you consider values, normal edit distance bounded by threshold k. Okay, so here you are considering values between 0 and k in your dynamic programming table. You are considering diagonals s between minus v to v. Why? Because like if the value v can only appear in diagonals from minus v to v. And if you're considering diagonals beyond that, the starting values in those diagonals will be higher than v. So you just need to look at diagonals from minus v to v. And for each diagonal, in that range, you compute the highest row with that particular value v. So for example, suppose you are looking at the main diagonal here, and you know the highest row where the value v equal to 1 has appeared is over here. And similarly for the 2 neighboring diagonals. Now you want to compute the highest rows in the diagonals minus 2 to 2 for value 2. So how do you do so? You look at the main diagonal. If you're here, you take a substitution and you come over here. If you're here, you do an indel and you come over here. Similarly, if you're here, you do an indel, you come over here. So for all these 3 cases, you come over here. Now your cost is 2, and now you want to do an LC1 query to move as far as possible without making any other errors. So that's what you do. You do an LC1 query, you reach here, and that's the maximum highest row that you can go in diagonal 0 with a value of 2. So similarly, you can compute the highest row for each of the 5 diagonals for the value of 2 and so on. So overall, like if your values are ranging from 0 to k, there are 2k plus 1 diagonals to consider. In each diagonal, you will make KLC queries. So overall, you will be doing a k-squared LC queries. For normal edit distance computation, you can do a pre-processing, linear time pre-processing, so that this k-squared LC queries, each of these LC queries can be answered in constant time. So overall, you will have a running time of n plus k squared. Now for exact EDA queries, we'll follow the same setup, except that now the values v, instead of going in an increment of 1, will go in an increment of 1 over a. So you will look at 0, 1 over a, 2 over a, 3 over a, up to k. For every value, you will look at the diagonals. They don't change from minus v to v, because for indel, you are paying plus 1 for every indel. And now for every diagonal, you are again computing the highest row with the value v. Same logic using for the exact edit distance computation, just with these more different increments of 1 over a for the values of v. So that gives you the exact EDA computation. We show that this algorithm is the best that you can do in terms of conditional lower bounds. Now for approximate EDA. So how do we modify the exact EDA algorithm for approximate EDA computation? So the first thing, instead of going through all the values 0, 1 over A, 2 over A, 3 over A, we increment these values with a gap of epsilon. So we go in an increment of 0, epsilon, 2, epsilon k, because anyway we can observe this epsilon gap in our approximation factor. And another point is, instead of doing the LC1 queries, as I have told you, like epsilon A substitutions are free. So we will be doing an LC epsilon A queries. And also like we can do an approximate LC epsilon A queries, approximation like by a 1 plus epsilon factor, because anyway, we are allowing 1 plus epsilon factors. So that's the main change. You are going through in a coarser granularity for the values V. Instead of releasing exact LC1 queries, you are releasing approximate LC epsilon A queries for every diagonal. And that should help you in speeding up your running time. So that's the overall algorithm to get a 1 plus epsilon approximation factor for EDA. So the main technical challenge is like, how do you do approximate LCD queries? D will be epsilon A. So LCD queries within 1 plus epsilon factor very fast. To do so, we'll be using a sampling technique. So let's look at some ideas like for a sampling algorithm to compute approximate LCD queries first. Here we should note that for LCD queries, the maximum sampling rate that we can hope for is 1 over D, because we have to catch one error, right, out of D errors. So really we cannot expect to have a sampling rate lower than 1 over D. So suppose I sample X at a rate of 1 over D, and then we return the first sampled I such that X plus I is not doesn't match with Y plus I. We have these small x and small y positions from where we are computing this LCD query. Okay, so that's fine. But then what is the sampling rate are we looking at in Y? For every position, sample position in X, there are k possible shifts to consider. And that means the sampling rate at Y that we are looking at is k over D, which is too high. So this naive sampling rate doesn't give you the ideal sampling rate of 1 over D for X and Y. Another way to get uniform sampling from X and Y could be that you sample X and Y at a rate of 1 over square root of D. In that case, X plus I and Y plus I, they are together sampled with probability 1 over D. So you can compute LCD queries, but again, the sampling rate is 1 over square root of D, which is way too high than what we are expecting, a sampling rate of 1 over D. GCAS 19, this is a paper on gap edit distance from Fox 2019. They also needed to compute approximate LC queries, not LCD queries though. So they wanted to compute LC1 queries with an approximation factor of D. So for that, what they did, whenever they are starting from a particular position X and Y, in capital X and capital Y, they have a waiting period. In this waiting period, they look at all possible shifts where the matches are exact. And that helps them to eliminate some other shifts because they are really looking for LC1 queries. So for all those shifts where there is at least one error, they can eliminate those diagonals. And for the other diagonals, in the waiting periods, the two strings X and Y are matching exactly. So once they match in the waiting period, and there are multiple shifts where they are matching, that implies the strings are periodic. So then instead of trying for every possible shift, which was a problem for our naive sampling method, they check for periodicity. And once the periodicity breaks, then that means there is a potential mismatch. And that's how they can get a 1 over D sampling rate. So we want to use their idea, but there are multiple bottlenecks here. So first of all, in the previous case, in GCAS 19, whenever there is a whenever there is a particular shift where there is at least one error in the waiting period, you can eliminate that shift because they are looking for LC1 query. We cannot do that. We are looking for LCG queries. So even if there is a shift for which there is a mismatch in the waiting period, we cannot eliminate that. So which means we have to handle with, like, even in the waiting period, we are really looking for almost periodic strings, not periodic strings. So we have to handle almost periodic strings, and not every period break is a mismatch. So these two make our methods, make our algorithms much more complicated to handle almost periodic strings where every period break is not a mismatch. So overall, this is the comparisons that we get. The fourth row is our work. So we get a 1 plus epsilon approximation factor. We are returning LCD queries with 1 plus epsilon approximation factor. The pre-processing time is n over d. So we do get 1 over d sampling rate. We have a query time of order of tk. This is basically you have to spend some more time for every period break in order to explore the local regions there to find for mismatches. Whereas in GCase 19, they can only answer LC1 query. They have order of d approximation, much higher approximation. Pre-processing time is n over d, which we match. Their query time is faster. On the other hand, LCG queries, the only other work that can answer LCG queries with 1 plus epsilon approximation is BCR 20, but they have a much higher sampling rate, though they are, but lower query time. So overall, this is the trade-offs that we get between pre-processing time and query time for LCDXY, and that helps us to get our running time of n over a plus AK cube. Open questions. The main open question is, can we improve the running time of our algorithm at the expense of worse approximation factor? So here we are looking for 1 plus epsilon approximation factor. For normal edit distance, we do not know such approximation factors in sublinear time. Whereas we know how to have better running time there. Like we can get rid of the poly-k terms for normal sublinear time edit distance computation. And we also know how to go beyond n over a, like when we are looking for higher approximation errors. So the question is, like, can we also do those things for when we are looking for EDA? Can we get better running time, maybe with a worse approximation factors? Okay, so thank you for listening.